All right. Thanks for waiting, guys. Today, presentation by Yigit Alparslan. Yeah. Attention is all you need. So this paper was, I think it was released in 2017.
It was submitted to the archive in
18? Oh, okay. And in the past 2 years, it's gotten over 5,000 citations. I'm just looking for a place. Okay, I'll just take a box. So take it away.
Yeah, it was submitted to archive. Archive is not fully peer reviewed, but it got so many citations, and it was pretty groundbreaking research that was done by Google Brain and some collaborators from University of Toronto. Today we're going to talk about it. So last week with Esam we talked about attention as a function of fatigue, and this also attention, but not this is completely attention concept. And I guess you could make some connections as we go along, because the model is going to be paying attention to some words in the sequence in its input. But yes, it's different. It's different from the biological sense. And okay, let's get started. So I'm gonna click define some words because I want everyone to be on the same page. And I'll talk about the general problem statement, and then we'll talk about why this paper is novel, why it got so many citations. So we'll compare to the classical solution. The classic being old NLP up until I think 2014, so it's not that old, it's pretty recent. Like if the classic solution is also pretty recent, but this paper's novelty is going to be even more groundbreaking than that. And then transfer network is one aspect of the paper. It's like one of the main aspects. We're going to talk about the architecture and implementation, and it's going to be a deep dive into architecture then, and I'll talk about the results. So I'm not doing NLP research, and this is not my research. So to read the paper, I have to go check some blogs and Casa, right? Yes, you suggested me a blog. That was really helpful. A couple of YouTube videos talks about this. They were also really helpful. So the credits should go where they are due. So all the figures are from this blog post. This gentleman called J. Alamar did a really nice job of explaining it. If you want to take a deeper dive, you should definitely check that blog post. And then this gentleman, Joseph Palermo, also talked about this paper in an event hosted by AISC. Let's get started. So the paper talks about this sequence transduction. I believe it's just a fancy word to say like it's a sequence problem. So we have a mapping problem where we try to map an input sentence to an output sentence. It's a sequence to sequence problem. And the transformer network that we're going to see is trying to solve this. Which leads us to the second definition, the transformer model. It's a highly complicated model of encoders and decoders to solve this problem. Second definition is machine translation. That's what Google Translate does, trying to translate one language to another. In all of these problems, you're going to see tokens. They're like the units in our problems, and they can be words, subwords, characters in our sequences. So attention is what we need, and the short definition is flexible context. That's my definition actually, but I think it makes sense. But the actual definition given by the paper is this formula that takes queries, keys, and values. Those are some abstracted values, some abstractions taken away from the sequence, input sequence, and we're gonna make sense out of it later. So, and the long definition is that the model is going to try to attend to or pay attention to the hidden inner states of the input sequence, and that way it will give a better result compared to the one that's been done so far, which is the classic approach. But yeah, this is just a short definition and some definitions that I just wanted to clear out in the beginning, and then we'll define it later. Yes.
I have a quick question about the attention. So it's using a softmax. Is it sort of like you have like 5 words and you use a softmax to create a probability distribution over each 5 word to see which one of the word you want to focus on?
Yes, definitely. So,
Okay.
So the authors are using softmax because they want to create a PDF out of the tokens or ordered words, and softmax helps them do that because the input might be all over the place. It might be greater than 1, like let's say less than 0. But when you apply softmax, each of these real numbers that were inputs now have to be numbers that add up to 1. So their sum has to be 1, and there had to be a number between 0 and 1. So it creates a probability distribution function. So we have RNNs. We're still in the definition part. It's a sequential model, and one of the main takeaways from this paper is that it's going to eliminate the limitations that come with the sequential model. We have embeddings, and they are just a way for models to understand words. So you go from the string domain to a feature domain, feature vector domain, where each embedding is just a representation of the words. And you have the softmax function, we just defined it. It creates a PDF out of inputs that might not be probability inputs. And its formal definition is here. So up until this point, we've seen recurrent neural networks, LSTMs, to do the sequence-to-sequence problem solving, and they were established as state-of-the-art in sequence modeling, to do NLP, to do entity detection, to do parsing. So they work on the positions of the input. So to be able to get the output at, let's say, t plus 1, you have to be able to solve the output at t. This was also hard for parallelization, and this paper is also going to mention that with their approach, with their new architecture called transformer networks, they're able to apply parallelization. So the RNNs, they work on the relative position of each token, the sequentials, and can you imagine? I'm going to yield this question to the floor. Could you think of any any other limitations, or any other better ways of doing the sequential modeling? Of course, the answer is this paper, but any comments on this?
Yeah, the RNNs need to kind of encode everything in a pass into a single state
Right.
proceeding. So
Yeah,
I think that's a limitation that is needed. So
definitely. Yeah, the moment you, yes, you have a question.
Oh, I have another limitation.
Oh yeah.
Well, so one of the big issues with RNNs is that at each time step when it takes in a token, it's computing a new memory vector, right? But theoretically, mathematically, it has the potential to remember everything from the past, but in practice, it doesn't. It notoriously is not good at maintaining a good memory state, which is something that this paper also addresses.
So it's more of a short-term memory than long-term memory.
Yeah, LSTMs really do help with that memory problem, but they're still not perfect. They still have a lot of issues and suffer from forgetting.
I can mention another one. So since this is sequential, the number of sequential computations that you need to do increases with the input size. So if you have a bigger sentence that you're trying to embed, of course it's going to cost more computations. Yes.
Oh yeah, didn't they say you couldn't do parallel processing with RNN?
Yeah.
That's what you do.
But so on the other side,
with the transformer network, you have to specify the size of the matrix that you can. So it's like 2,000 by 2,000, right, or something like that.
Yeah.
And you can't go beyond. Well, you would increase the size of the matrix, but RNNs essentially have an infinite history, right? So you can put any length of sequence in it.
And it's a trade-off.
Yeah.
Anything else? Okay, I'll keep going. So in the definition section, we define the mapping problem. So yeah, the problem that this paper is trying to solve is sequence-to-sequence problem. You have an input sequence and you want to map it to some output tokens in your sequence. So to get that output sequence, you have to be able to, given an input, produce a probability distribution values over some tokens, and then pick those tokens in the correct sequence. So if you want to translate an English sentence to German one, you need to have an English vocabulary, a German vocabulary, and then you need to have those tokens in the German vocabulary. So when you create the probability values over some tokens in the German vocabulary, you need to also be able to pick them in the right sequence. So the order is very important because it's a sequence problem. Another other domains that this might be also helpful is listed. Other domains are listed here, so you might also do like entity detection, because if you could map them in the correct order, then you could also parse it. You could also help with tagging. So it's a broad problem, but this paper only focuses on one aspect of it, which is the sequence-to-sequence problem. The classic solution up until this paper has been the following. It's a RNN approach where you have a fixed context. That's what the authors mentioned. So, and then the attention was defined as a flexible context, and I will define it later. So if you have an incoming, let's say, sentence, and if you have a chat bot, and if you want to produce an output, the incoming input might have to give you a first thought vector, which is then given into the decoder. And we're going to see this idea over and over again. So the output of the encoder is going to go into the output. It's going to become an input to the decoder. And then so those words that are like yes was out with the end of sequence token, it's called AND, have to be produced. And the RNNs, they have to be aware of the timestamps because the order matters. And once you get an input, so first you create embeddings, and then you put them in a representation vector, and then your encoder is going to put them in a finite fixed vector, and then which is going to be decoded later for the outputs. That was a classic solution. I still haven't started talking about the paper's contribution, so this is all being classic solution. And since you have a sequence problem where you're trying to solve the t+1 with the t output, this prevents parallelization, which is going to be solved with transformers networks later. So now we start with the paper. So they use this attention state. It's this hidden states, and they encode the input states in this attention layer, and they attend to, or they pay attention to those hidden states in the input to make sense out of the output in a much better way. So yeah, when decoding the output of the input, the output of the attention layers is going to go to the decoder. Any problem? Any questions on that? And then so right now the attention is a black box. we don't know what's inside, but we will know in a couple of slides. So authors define this transformer network. It's two stacks of encoders and decoders, and there's some hyperparameters that they had to decide, and I think they decided based on some experimental values, so they tuned those values. But those two stacks are the transformer network, and in each encoder stack, you're gonna see sublayers of, and each encoder stack, you're gonna see sublayers as well, and also you're gonna see that the output of the encoder is gonna go to the decoder, so it's gonna become an input to the decoder, and the encoder and decoders are gonna use attention layers in these stacks. So the encoder contains sub attention layers, and sub attention is a sublayer in encoder. So right now you can see there are 6 encoders and 6 decoders, and I want to ask you, do you know why 6 might be chosen? Is it on purpose, or is there any value based on this input? Yes.
Because 6 was just chosen based on like experiments. They probably have quite a few experiments. And
Yeah, it's one of the many hyperparameters, and they just tune it based on experiments, and 6 was chosen. So it's not like a magic number, but it's just an experiment design decision. So in the stack, the last encoder is going to produce inputs to all the decoders. And then now we saw the first stack of encoders, we saw the second stack, which was a stack of decoders, and then we saw that each stack has 6 of them, encoders and decoders. And then these encoders also is gonna have sub elements in them. Because as you can see, we haven't seen the attention part yet. But one thing to notice is that it's not using convolution or recurrence. So now we start digging deeper. So each layer, so now in the encoder part, so there was the first stack full of 6 encoders, and then now we pick one encoder, and now it's inside that encoder we're gonna see 2 sublayers. So now this is the first time we start to see attention. So that sub-attention sublayer, and then there's a feed-forward neural network, and that feed-forward neural network is gonna be used. That's going to be the same for all the encoders. And I think one reason why they wanted to use the same, I might be wrong in this one, was because of convenience. And I think at the end of the day, the feed-forward neural network is just going to be another matrix multiplication. So they just use the same weights. So before digging deeper, I also want to just mention what an output of this transformer network would look like. So for given sentence, you might have, let's say, some pronouns, and all you're trying to do is to make a sense out of each of these words in terms of other words. And the words in your model might not be words, it could be also like tokens or subwords. But if you take this example, the left one, where you're trying to make sense out of the pronoun it based on animal or street, and then it's a tough problem because that pronoun might refer to, let's say, the animal or the street, and it's based on those weights that it's gonna make it refer to the animal word, not the street word. So you're trying to relate those elements in terms of other elements, and the more you pay attention to these weights, you can get better representations. So So this is the last time we left it. So it's an encoder that consists of a self-attention layer and a feed-forward neural network. And then based on the input, let's say a French input, you can have 3 words. So you convert them to embeddings and you give them as an input to the self-attention layer, which then calculates an attention score. So X values are words in your input sequence, and then the Z values are attention score for each of those words. So Z1 is a score calculated by the self-attention layer based on its representation with other words in your sequence. And Z2 is going to be another score calculated by self-attention layer in terms of the other 2 words as well. So the first one and the third one. So and then you stack those Z values, so you get a Z matrix. So that's your attention matrix, and then that gets multiplied by feed-forward network, and then it gets passed to the other encoder, which happens all the way to the top of the encoder, and then the last encoder is gonna have to give those outputs to the decoder, which is gonna take that as an input. So the attention is going to be determining how do you want to represent that value based on other words. And as you can see, so for each word, if you want to represent it in terms of other words, let's say the one and the third one, when you represent the first one in terms of the third one, and when you represent the third one in terms of the first one, you might say that you're actually doing some duplicate computations, which is intuitive, and I think, and that's the point where authors mentioned that there's some room for parallelization here, because at that point the intuition is correct, because when you calculate the X3 representation in terms of the other ones, you will have to do some duplicate computations, because you just did the X1 in terms of other X values. So that's going to be also another factor why this transformer network is a huge deal, because it took advantage of the parallelism. Any comments or questions?
Could you mention again how you get to the attention score?
No, we haven't. Yeah, so
You haven't.
it's still a black box.
Okay.
Yeah. So we started with just 2 stacks, and then we expanded on 1 stack. We still don't know how the attention score is being calculated, and then we just explored what an encoder is. Excuse me. And then now we explored the roles of self-attention and feed-forward, and then now, yeah, it's going to be more clear in a couple slides. So the paper kind of skips this, but I think the blog posts and the talks were helpful. So to calculate a self-attention score given an input, the authors calculate 3 things, and these are abstractions. Like the sequence is abstracted away into deeper bits of information. The first one is a query, the second one is key, and the third one is value matrices. So given an embedding, input embedding, you are going to abstract away these 3 values, and this is going to help you calculate this stuff, the attention score downstream. So given an input X, you pack the weights of query, key, and value, and you multiply them to get the query, key, and value matrices. So the weights, when they multiply by the input embeddings, they get you these 3 queries, these 3 matrices, and then those weights come from your training. And I have an odd example of what a training might look like. So now you just created your 3 matrices, and so you're going to use them. So you might say, like, why are we doing this? It's because given an input, we want to calculate an attention matrix. So three metrics that you calculated before is gonna help you calculate the z-score. And as I said, the attention is just a score for each word. It determines how much focus you want to place in that word with respect to others. So it's a representation of that word in terms of other words. So this was the attention definition that you saw in the first slide. The query matrix, Q stands for query, and then key and values are the matrices that we just calculated by multiplying the input with those weights. And then you scale it by dividing with root of pk, which is the dimension of the key. So in the paper, they use dimensions of 64 for the key and values. So root of 64 is going to be 8. So the result of the matrix multiplication is divided by 8. And then you do softmax on those each results, and softmax is going to produce a PDF. So Z is going to be the PDF values distributed over your output vocabulary. So for each token in your output vocabulary, you're going to assign some probability values for those tokens, and that way it's going to create your sequence, output sequence, because then you will know which one to pick. And I don't know if you've noticed, but with this formula you can get the PDFs out of tokens, but we haven't talked about the positions yet. So you can get which token, you might know which token to get, but you still don't know the order. Because the matrix multiplication, when you do these, we don't preserve the location information yet. So the attention is going to help you how much value you place for that word in terms of other words, but we still don't know the position. And I don't know if you've noticed, but that's just a big right now caveat, because we want to create an output sequence. We know which tokens to use, but we don't know the order yet. So the order part is also important, and the authors do a trick to figure out the order. But right now we're just doing the attention problem, so we're trying to represent it in terms of other words and doing the softmax over these three abstract pieces of information that are query, key, and value is going to help you calculate this z-score. And also, so we just calculated the attention score, but we haven't seen the order yet, and also we haven't figured out the parallelism yet. So these two things are still in the agenda. This is a better representation of how you calculate the attention. So let's say you have an input that is just of length 2. So input starts with thinking machines. So it's just 2 words, right? And it's a pretty short input sequence. So we'll also talk about how it might scale up when you have a longer sequence. But for each words in the sequence, you create an embedding. So that's your x1 and x2. And I'm just going to go back to remind you that these x1, x2, and x3 are also in the staff attention area. So based on these embeddings, you abstract away 3 values, three bits of information that are queries, keys, and values. And one thing to notice is that they have smaller dimension compared to the embedding. So that's another thing that we have to talk about, that we might be losing some information when we do these abstractions. But right now we got the query, key, and values. Based on the definition that we just mentioned, you can calculate a score. So I'm going to go back again, and this is the formula that you use. So here you calculate the score by multiplying it, and you scale it by dividing by 8. It's 8 because the dimension of the key, a vector is 64. So 112 divided by 8, you got 14. 96 divided by 8, you got 12. And then you pass some softmax values over those outputs. So now you got probability values over those input values. And we have to also multiply by value because there was a definition in advance. So when you multiply the softmax output with V, you'll get a Z score. So Z1 is going to be an attention score for thinking, the word thinking, and Z2 is going to be an attention score for machines. And if you stack Z1 and Z2, so concatenate them horizontally, you'll get your Z matrix. So if, let's say you had 50 words in your sequence, so then you would have to do this 50 times. So it will start from Q1 and go up until Q50. It will start from K1 and go up until K50. So you will have to do this all the way from for Z1 up until Z50. That's how you'll scale it up. So Z1, is everyone with me? Everyone have questions? Yes.
Well, no. Did they talk about? So this is a self-attention layer, but you're paying attention to your own. I think softmax here is 0.88 for its own word.
Yeah.
So do they talk about like not paying attention to yourself?
I think I don't think they. Yes.
So you do wanna pay attention to yourself with this because like in general the query key value is like a very general paradigm where like let's say you had question and answering, your query might be your question and your key and value might be your representation for where you could potentially get the answer, like a paragraph or some sort of document. So in general what you'll do is you'll take this query times the keys to produce the softmax, which gives you these values that you can then use to take all of your values that you have and create a weighted average of them. So in something like this, where you want to pay attention to yourself, you might want to weight really strongly what you just were and gather a little bit of information from the other surrounding vectors. So it's important for particular machine translation that you do pay attention to yourself.
I think authors skip that part fast, but I think they saw benefits. And the way that I think about it is that 0.88 is your reference. And if you have a value like 0.12, you might say, okay, what does 0.12 means? But you have a reference which is 0.88. So you can say, okay, it's as important as like 1/4 or 1/5 important as my own word, which is thinking. So yeah. And we haven't still talked about the positional reporting. So we don't know. So we just calculated what machines word might value in terms of thinking and what thinking might be valued compared to machines, but there's no position information yet. Yes.
What's the shape of it? Like, what dimensions do the matrix X have?
So for an input like je suis étudiant, which is the French word for I'm student, it would be 3 rows, and I think the embedding size is about 256.
Oh, okay, so
Yeah,
it's
so it's 256. It's 3 by 256, and the embedding is gonna have a dimension that's gonna be determined by the authors, or I think they use the standard embedding library like Word2Vec, yeah, which is really popular. I think it was implemented by Stanford. I might be wrong, but they use those standard embeddings, and in that case, they had a 3 by 256 dimension, and then they stack them. So that's your X vector.
so it's like the length of the past sequence times the encoding size, basically.
The past sequence, no, embeddings are different right now. So X1 embedding has no idea about X2 embedding yet, right?
But the size is the encoding size times the kind of number of words before.
Number of words times embedding these dimensions. Yes, that's the ultimate dimension of your X vector or matrix. Okay, so we talked about how we would scale up. We talked about how we would calculate Z1 and Z2. Now we have to talk about the position also. We just mentioned that when you go from embedding to those three apps, yes.
So the softmax output is just over the input space, right?
Yes.
It's not over the possible dictionary of possible outputs.
So this is
You never pay attention to something not in your input. Is that right?
Yeah, that's correct. Yeah, I was just saying, we talk about how we will be calculated and we scale up, and we also just mentioned that we will do some function. When you go from embedding dimensions to those three abstractions, which are queries, keys, and values. So we have to mitigate that one too. So to mitigate that information loss, authors define this concept called multi-head. So since embeddings are larger, have a larger space, abstractions you will not be able to hold everything. So it's going to result in loss of some information regarding your input. So they define this multi-head, and this is the place where they start doing the parallelization optimization. So for each X, they're going to repeat it for each. So for each xi, I was saying that if you remember that when you calculate the x3 representation in terms of x1, you might have already done that some of that computation when you were calculating the x1 representation in terms of x3. So this is where the multi-head comes. So they pick a number, in that case 8, and they're going to do it over 8 times individually but separately, and then join them to get the same dimension of Z. So they take the input sentence, they create the embeddings, and then they create these 8 heads. So each head, in this case, is going to be learning, that's what they say, learning one task, one separate task about the input. So when you have 8 of them, there's 8 multiplications. So 8 heads is going to produce you 8 different z-scores, which can be joined to get your same dimensional z matrix. So for the first words, you still get the query key and values. You calculate the softmax for those same word, and then you calculate the score for the same for the first word to 0. So now you do it for each word. Each weight, I'm sorry. So once you calculate the attention, it's gonna be resulting in a z matrix. But that z matrix, when you join all of the z values, it's gonna produce the same dimension as your previous z matrix. And then the blog post was mentioning this R value, R matrix, if you can see here. And I don't think that's relevant because there is no use out of it. So you can just assume that it's irrelevant. So since each weight matrix is being multiplied separately, this is the place where you could just do those multiplications separately on a GPU. So then you can improve the performance. So for this case, the head number was 8. So for each head, you were producing 3 matrices, query, key, and value. So for this one, you're going to be producing 24 of them. So it's 3 sets of matrices. And then to be able to understand or to be able to aware of the position of the words in your input sequence, the authors did this trick where they just add some encoding that the model learns. So now each embedding is going to have some positional value. So then everything that we've done so far was mentioning the triggers without these positional encodings, but once you add those values, then you can be aware of the positional encoding of your words in your input sequence. So if you go away all the way back, this is from X1, there was also actually position value. So just to recap, we first started with encoder and decoder stacks. And then we saw that each encoder would have a self-attention layer and a feed-forward neural network. The self-attention part was the one layer that was calculating the attention scores based on embeddings. And it will pass it to the feed-forward network, it will be multiplied and it will pass to the other encoder. We calculated how we would get those three matrices to a key value, and which would then help us calculate the softmax, the z values, which are the scores. And then we also mentioned that the trick was to add those positional encodings, so that now you're aware of the space. So the authors also mentioned this residual connection. So for anyone who's familiar with ResNets, the idea is that in a ResNet, it's easier to calculate, let's say, x plus f, where x is an identity function, compared to f of x. So, and we have that structure where you have some function and some identity value, which are the positional encodings. So, because we just added the positional encodings, so that's where they take advantage of this residual idea. So we calculate these z values from the self-attention layer, and then they got being normalized because you have an x embedding space, and then you add some more information on it, so you have to scale it or normalize it, and then you multiply feed forward to the feed forward layer, and you use the same weights for each score. So it's just the same matrix being multiplied with the z values, and then you pass it to the other encoder. So if you have these simple thinking machines, once you add the position encodings, you calculate the z score, which then gets passed to feed-forward neural network, which have the same weights, and it's passed to the next encoder. So the overall entire transformer network that you see, it has two stacks of encoders and decoders, and it uses the same feed-forward network's weights, and each layer calculates the attention score for the embeddings, and passes to the other encoder. And then the top of the encoder is going to be producing the input for the decoders. And those output, the key and values are, as we've mentioned, bits of information that were abstracted away from your input sequence. And they have less dimensions than your embeddings, which results in information loss, so you do multi-head to mitigate that. So the entire network is going to look like this, where you use the same feed forward and you just calculate attention for each encoder. And only the last encoder output is going to become an input for the decoders.
Shouldn't that be number 6?
Yes, it's actually 6 and 6, but just not to repeat the same thing. This is a figure that was just done by 2, but and that's just a hyperparameter. So based on the input, you could pick something else and just experimentally tune it. Yes.
It's the last softmax of the entire vocabulary, like all of it. For the final softmax after that,
You mean like the entire English or French vocabulary?
yeah, like of the entire.
That shouldn't be because the model, actually, all the self-attentions, yes, that's a good point. All the self-attention sublayers is going to be using softmax for the input sequence or the output signal of the previous encoder. But finally, I have also an example where you will calculate a probability distribution. You have to be able to pick the ones from your vocabulary, right?
Yeah.
So then in the decoder stage, it has to be applied to entire values, which is only once. So yeah, this training model, so you have this example and the expected output is I'm a student. So I think this is a better picture, so this picture is better. So the output vocabulary has to be producing those 5 words plus an end of sequence word, which the model also learns. So when the sentence ends or when the sequence ends, it has to be able to end it with this token. So it's one of the main tokens in the vocabulary. Nothing different. So it creates these PDF values over vocabulary and it picks the ones that are the highest. Any questions?
So
Yes.
at the end, there's one softmax layer. It picks one token, and then you have to run it again to get the next token.
At the end of the decoders produced vectors for each positional slot. Then you take each of those positional vectors, put them through a linear layer, and then for each of those, you're running a softmax to select a token for each of these.
So it's like 2,000 dimensional or something.
Yeah. Otherwise, without the vocabulary, without the training vocabulary, let's say you want to translate to German.
Yeah.
Without the German training vocabulary, there's no way for you to know what elements you would use the softmax to. So it makes sense to create once a very heavy computation where you do the softmax over entire vocabulary. And then that vocabulary has to have all the tokens plus an end of strings token. So some of the aspects that we have mentioned, we mentioned that there was some room for parallelization because the multi-head computation can have multiple and individual computations. So they're comparing these values in terms of the complexity of each layer. Also room for parallelization, which is mainly sequential versus parallel. And also when you create the computational graph, let's say, first 2 points in your computational graphs in terms of embeddings. Actually, it will be in terms of embeddings. It will be in terms of your learned weights. So if you want to go from furthest given a point, if you want to go to the furthest point in your training graph, what would be the maximum path? So they found out that for self-attention approach with the transformer networks, it wouldn't be dependent on the input size for the last two parameters. So the sequential operations wouldn't depend on the input size, and then the maximum path length wouldn't depend on the input size, which is a huge improvement compared to others. You're just mentioning that for recurrent, for example, if you have a longer sentence, then it's going to cost you more. And you can see that you can say with the running time big O of n. So these are the results that they achieved. So there's a standard way of evaluating these machine translations, and there is a conference every year that's called WM. And then so in 2014, they performed those two tasks, so English to German translation and English to French translation. So the BLEU score is a language study score is between 0 and 1, but they multiply with hundreds and kind of confuse me. But when they say score of 28.4, it's actually 0.28. And when they say outperforms more than 2.0, it's actually 2%. So they established as the new state of the art for those two tasks. And the last one, as you can see, they trained on 8 GPU models for about 3.5 days, 3.5 days. And then they got the score, which was better than the previous one. I was confused why they picked the 2014 tasks, because the paper was submitted in 2018. And I did some research, and I also looked at the tasks between 2018 and 2014. And to my understanding, just the languages and the training vocabulary size changes over years. So virtually there's no difference between 2014 and 2018, but just bugging and find a clear answer for that. But yeah, they are the new established models for those two tasks. I think we're almost done with time. Any questions? And also, I want to mention this. If you're more interested in NLP, there are some resources that I found. Definitely check it, or we could send this email, this PowerPoint to you as well. Any comments or questions?
We probably did 2014 just to have the standard data set. So next week, Coast presenting on reinforcement